So one algorithm which is used a lot in quantum computing and also in quantum cognition is the quantum walk. So this is a quantum version of the classical random walk model. And the random walk was first described by the statistician Carl Pearson in a 1905 paper as using the example of a drunken man who takes a step in one direction and then another step in a different direction and so on. The expected distance traveled is seen to grow with the square root of time, but the most probable place to find a drunken man who is at all capable of keeping on his feet is somewhere near his starting point. The same idea had actually already been used by Louis Bachelier in his 1900 thesis on option pricing to argue that an investor's expected profit or loss was zero because prices move randomly up or down, but the best forecast for an asset's future price is its current price. So the classical random walk, the way this works is you can model it using a coin toss. So if you toss the coin at each time and you move to the left if the coin is tails, and move to the right if it's heads up, and just repeat this many times. And what you find is that so one path might look like this one here, and then you find that there are more ways to get to the circles at the center here, and the only way to kind of get to one of the extremes, like down here, is to toss get the same result at each coin toss, which is very unlikely. So we're going to end up with kind of a peaked distribution in the middle. And the random walk, so it was first used to price options, then it was used in nuclear physics, and then it fed back from there into finance again. And now it's ubiquitous in finance, and it forms the core of all the models used to calculate things like the price of options and financial derivatives in general. So here's a quantum circuit which does something a bit similar, and it's one we've already seen. So it's a Toffoli gate followed by a controlled NOT gate and a NOT gate. And as we saw, what this does is it increments a counter. So this we have the different binary representations of 0 to 7, and it just increments them by 1. And you can think of a larger, so you can think of this as kind of stepping up, so taking a step in one direction. And there's another version of the same circuit which has the controls turned around, so they act not when the qubit is in the true state, or the zero state, whatever, but when it's on the opposite of that. And then you get the you combine these two, so you've got incrementing, decrementing, and down here on this qubit we've got a Hadamard gate. So this puts this into a superposition of 0 and 1. So we're going to, the part of this gate which is in the state 1 is going to increment, and the part which is in 0 is going to decrement, and the result of all this is going to be what looks rather complicated when you write it out in terms of the mathematics, but when you see it in terms of the quantum gate, it's a fairly simple idea. It's basically you're kind of splitting off your starting point in two directions, and you're keeping track of part of it which is, let's say, heads up, part of it which is tails, and you're acting on each of those parts, either incrementing or decrementing depending on the state. And so the net effect, so one thing is there's nothing actually random here. There's a wave function which is evolving over time. The only random part comes at the end when we collapse the wave function down, when we measure it. So that's a bit different. The other thing that you can imagine is happening here is that because we're kind of splitting off this wave function, we know with quantum stuff that we get interference. So we've got these different paths that are kind of coming down here, and when they meet somewhere, they don't have to add together, they can subtract from one another. So what we're going to see, we're going to expect to see some interference patterns, and what you get, the distribution that you get is quite interesting. It's very different from the classical one. So the classical one is this normal distribution. So the random walk converges to the normal distribution for many time steps. The quantum walk, you got this thing I'm calling the paranormal distribution, which is very sort of has these strange peaks on either side and is actually quite low in the middle because of the interference. So so this is interesting, and it's kind of, you think about it a little bit. So in sort of traditional finance theory, we're always thinking about everything being normally distributed. So this idea that prices stay close to their starting point and they're kind of nicely, but this is very, so that might be objectively fairly close to the truth. But when you think about the mental frame of people who are thinking about prices, it's quite different. No one who buys options, or I think most people buy options anyway, on a stock, they aren't thinking about that stock staying at the same price it is now with maybe a small chance of a deviation which only grows slowly in time. They're going to be thinking about either increasing by a certain amount per year or decreasing by a certain amount per year, kind of stretching out in this kind of linear fashion. And they're going to be kind of holding these two ideas. So they might be kind of biased towards one picture or the other, but they're also going to be kind of holding the opposite picture in their head at the same time. This picture here shows a sequence of probability distributions for the classical random walk. And so you start at the center here, one point which isn't shown, and then it gradually kind of, the probability spreads out over time. But you notice with the classical one, it's very sort of smooth and ordered, and with the quantum one, again, we're starting off in the center, and then the probability is spreading out, but it's much more rapid. We've got this kind of shock wave, which is like speeding out in either direction. And actually, this is a feature of the quantum walk, which is one reason why it's used a lot in quantum computing, was because it sort of traverses a lot of ground very quickly. Now, we can make the quantum walk act in a more classical fashion if we want, and through decoherence. So decoherence is basically when you get some random noise added to the quantum calculation at each step. And quantum decoherence is sort of the enemy of quantum computers, because they make the quantum computers behave in a less quantum way. They make them behave in a classical fashion. So a big part of the challenge of quantum computing is to isolate the qubits from their environment so that they don't get this decoherence. Now we can add some decoherence to a quantum walk model quite simply in the algorithm, just by adding some random noise. And then what we find is that if we add enough decoherence, it basically just converges onto the normal distribution. But is this what we want, or do we want to be able to exploit this quantum properties in some way? So in quantum cognition, the quantum walk model has been used to model various cognitive effects, including signal detection, how people assign ratings to stimuli, and general decision making. In terms of neural processes, you can think of it as modeling a kind of a parallel cognitive architecture. It involves both cooperative and competitive interactions. So you're going to be getting this kind of interference types of effects. So it's as a model of how we think about the future, it seems like an improvement over the classical random walk model, which is really more a model of something like a dust particle, which doesn't think about the future. And later on, we're going to be using the quantum walk to model subjective beliefs about future asset price changes, as opposed to the actual observed changes, which are not the same thing. So, again, if people expected prices to be normally distributed, why would they buy stocks or options in the first place? And we'll be returning to that question.